Hello everyone, welcome to my YouTube channel. And in this channel and in this specifically in this series we are working on the simulation and our coding skills, how we can improve it specifically for vapor compression cycle, which has application in HVAC and refrigeration. So let's move on. In the previous video you have seen we have worked on loop. So we have made a single loop in which we increase the evaporator temperature, and we saw how the different important parameters like COP, compression ratio, mass flow rates, and compressor discharge temperature varies. So in this video we will work on the multiple looping. So what is multiple looping? What we will do, instead of just changing the evaporator temperature and its change on these parameters, now we will change the condenser temperature. We will also change the superheating, we will also change the subcooling, and we will also change iso-entropic efficiency of the compressor, and we will see how all these changing parameters affect the COP of our system. So let's start, and we will ask Grok to please modify this code to have multiple loops. For example, change evaporator temperature from -10 to 20 degrees Celsius, condenser temperature to, you can say, from 40 to 60 degrees Celsius, superheating from, you can say, 0 to 10 degrees Celsius, subcooling from 0 to 10 degrees Celsius, and iso-entropic efficiency from, you can say, 100 to 40%. And plot how COP changes while changing these parameters, right? And provide results in one window. So you can say it's a bit extensive requirement which we have put. So let's see how Grok works it, or it understands it or not. I will modify the vapor compression cycle to include multiple nested loops over the following parameters: evaporator temperature, condenser temperature, superheating, subcooling, isentropic efficiency. The code will calculate the COP for each combination of these parameters for these refrigerants, and using all these things which it was using before. So let's see. It is writing our new code, and we will just copy this code and we will run it in Python environment. So here you can see it has nested the loops over all parameters. So what it is doing is, for devaporation, in devaporation range it has defined, and then changing condenser in condenser range, then superheat in superheat range, and subcool in subcool range, isentropic efficiency in isentropic efficiency range. So here you can see these are the different loops in which this program will now run. And then here you can see it is plotting it, and it is giving us different plots like COP versus superheating, subcooling versus isentropic efficiency, and some summary of the plot. So it has completed, so just copy it and we'll make a new file. We will name it Grok 6. We'll paste this code and we will run it. So let's see, has it worked successfully or not. So here you can see the loop is running, but there are some error messages also. So let's see what it has done and why the error messages are coming. So here you can see it has provided us the average COP values with the evaporator temperature, and then with the condenser temperature, as the condenser temperature is increasing, it has also provided us average COP values. And here again, as the superheat is increasing, you can see it has provided us how the COP varies. Here you can see when the subcool is increasing, how the COP is varying. So these are very some interesting results we have got, and how the iso-entropic efficiency of the compressor is increasing and how the average COP is increasing. And here what it has provided us, it has provided us the range of COP values. For example, for R134A, it is telling us that the COP is varying in the range starting from 1 to more than 12, and similarly for R410A, R32 and ammonia. But it seems like there is some error in this code, because we cannot see the COP values increasing more than 6 or 7. So how it is like telling us like these COP values are have the values up till 13.27 and 13.19. So it seems like there is some code issue or some error which it was displaying while it was running. And also it is giving us the average COP value, so we don't ask it to calculate some average COP values. So maybe there is some issue in the code. Let's see and check what the code is. But what actually it calculated wrong is that it did not put all other things constant in a way. For example, the evaporator temperature should be fixed for every parameters. It should be like 0 degrees Celsius, or condenser temperature should be fixed, and superheating and subcool should be fixed, and just it has to change the isentropic efficiency. But what I think it has done, actually it has also varied these things, these parameters which should be fixed, it has also changed them, due to which it has calculated the, you can say, average COP values. So this is not our desired, you can say, the results, so we have to modify the code. Let's go back to this and provide some clear instructions. Please modify it so that when you are varying evaporator temperature, just keep other things constant and vice versa. So here we have asked him to verify it. So now it says the evaporator COP by varying each parameters. These are the parameters one at a time while keeping other constant at baseline values. So this is what actually we wanted. And so as I told you before, like we have to explain him clearly what we want, otherwise it misinterprets us and it calculates something different which is not desired. So this is what it do, it run different loops within a loop. So what we need, we have to run these loops separately, not looping all these 4 or 5 things together. So now you can see it is giving us different loops. For example, this is providing us the first loop in which it will vary the evaporator temperature while keeping all other things constant, and then it will run the second loop in which it will change the condenser temperature and other things will be constant, and then the third loop in which it will vary the superheat and so on, subcool, and then so on, isentropic efficiency. So this is what we wanted, and then it will also save the results to Excel, and now it is writing the commands for plotting the COP values versus each these things, and like COP versus the evaporator temperature, then COP versus the condenser temperature, and then COP versus superheating, and then COP versus subcooling. So here it is, it seems like correct code which we desired, and then let's copy it and paste it on the same code. Now we will run it and see what are the results. Are the results desirable? Now here you can see the results. So here we can see how with increasing the evaporator temperature the COP is varying, and here we can see that the R134A and ammonia, they are giving the highest COP values. Here we can see how with the condenser temperature COP value is varying. So again we can see ammonia is giving better COP values with the condenser temperature, and here we can see with increasing the superheating the COP value of ammonia is decreasing, whereas for R134A it is increasing. So it is interesting. All others are decreasing, whereas R134 is increasing. Similarly, here we can see with the subcooling, we can see all other refrigerants, they are increasing sharply, whereas this ammonia, it's not affecting that much, its gradient is not that much as compared to other refrigerants, and its COP is not increasing that sharply, whereas for other refrigerants the COP value is increasing. And here how the isentropic efficiency of the compressor is affecting the COP value. So here you can see as the efficiency is increasing the COP value is increasing, so it's always, it should be a increasing trend. So here you can see also the ammonia is also giving the highest COP values throughout the isentropic efficiency range. So this is what we want to see, how these different parameters are affecting the COP values in one window. So here you can see all these results, and you can just change the refrigerant names, and you will just get all others. For example, instead of R410 we want to see R404A, and instead of ammonia we want to see isobutane, and then we will just run it and we will see it. So here you can see the results. Now we have changed the refrigerants. You can also increase the number of refrigerants. You have to add another refrigerant name, and you have to write its color. So here you can see now the best is isobutene. It is having highest COP throughout these variables, varying these parameters like iso-entropic efficiency, superheating, subcooling, and condenser and evaporator temperature. So in this way you can just see how varying different conditions your refrigerant behaves, and this is what multiple looping is all about. So in just writing this code you can just see in a single glance which refrigerant is best. Thank you very much for watching this video, and if you like it, please like and subscribe my channel. And the code I will paste the code in the description so that you can use it. Thank you very much.